For thousands of years, humanity has explored the cosmos using only one sense: sight. From the first primitive telescopes to the advanced Hubble and James Webb, everything we know about the stars comes from light, electromagnetic radiation. But in 2015, everything changed. Scientists finally unlocked a brand new way to hear the universe. It's called Gravitational Wave Astronomy. Instead of looking for light, we are now watching for ripples in the very fabric of space-time itself. This isn't just a new telescope. It's like the universe finally found its voice. Today, we're diving into the mind-bending world of LIGO and the cosmic echoes of colliding giants. To understand gravitational waves, we have to look at the universe through the eyes of Albert Einstein. In his theory of general relativity, Einstein proposed that gravity isn't just a force. It's the curvature of space and time. Imagine space-time as a giant trampoline. If you place a heavy bowling ball in the center, the fabric bends. Now imagine two massive objects like black holes spiraling around each other at incredible speeds. They create massive distortions that travel away from the source at the speed of light. These are gravitational waves, literal ripples in the geometry of reality. They don't travel through space. They're the stretching and squeezing of space itself. The challenge with detecting these waves is that they are incredibly weak by the time they reach Earth. Even a wave from a massive cosmic collision changes the distance between 2 points by a fraction of a fraction. How small are we talking? LIGO, the Laser Interferometer Gravitational Wave Observatory, has to measure a change in distance as small as 10 to the minus 19th meters. To put that in perspective, that is 10,000 times smaller than the radius of a single proton. It is arguably the most precise measurement ever attempted by mankind. If you were measuring the distance to the nearest star. So, how do you measure something that small? LIGO uses an L-shaped instrument with two pipes, each 2.5 miles long. A laser beam is split in half and sent down both pipes. Mirrors at the ends bounce the light back and forth 400 times, making the effective journey over 1,000 miles long. When the beams return, they are recombined. If no wave is passing through, the light beams cancel each other out perfectly. This tiny shift causes the laser beams to fall out of sync, creating a flash of light that tells scientists something just happened in the deep universe. Because LIGO is so sensitive, it picks up everything. A truck driving 10 miles away or a small earthquake on the other side of the world can create enough vibration to ruin the data. To solve this, there are two separate LIGO installations, one in Washington and one in Louisiana. A real gravitational wave will hit both detectors almost simultaneously, while local noise will only show up in one. In September 2015, this system proved its worth. It detected the collision of two black holes 1.3 billion light-years away. In that final millisecond of their merger, they radiated 50 times more power than all the stars in the visible universe combined. This discovery wasn't just a win for Einstein. It was the start of a revolution. Gravitational waves allow us to see things that produce no light at all, like merging black holes or the internal structures of neutron stars. Every time humans find a new way to look at the sky, we discover something we never expected. With LIGO, we have stopped just looking at the stars and started listening to the heartbeat of the cosmos. The universe is finally talking, and we are finally ready to listen. For more mind-blowing space facts, subscribe to the channel. Until next time, keep looking up.